just need to share. But I need to be able to share.
I think you're the host now. You should be able to do it.
Is it?
Yeah, the host has been transferred to her.
Okay. So just a moment. Okay. So I will talk about automated program repair using formal verification techniques, and it's joint work with. Just a moment. I need to move the pictures some. Okay, it's a joint work with Hadar Frankel, Batchen Rothenberg, Corina Passareno, and Sarai Shenbal. So why automated program repair? In the process of software production and maintenance, much effort is invested in order to ensure that the product is as bug-free as possible. Manual bug repair is time-consuming and requires close familiarity with the checked program, and therefore there is a great need for tools performing automated program repair. In recent years, there has been much progress in this field. Most works on automated program repair are based on tests. They are given a set of buggy tests and a set of correct tests, and suggest a repair that correct the buggy tests and preserve the correctness of the correct test. We, on the other hand, use formal method techniques in order to do automatic program repair. In our case, we are getting a buggy program and a specification, and the goal is of the repair is to repair the program so that it will satisfy the specification. An important component of formal verification is model checking, where model checking gets a system model and a property, and it replies yes if the system satisfies the property and no otherwise. In the latter case, it also provides a counterexample, which is very useful for debugging, and we will also use it for automated repair. So what are we going to do when we use formal methods? We have a model checking that finds bug in the program, where a bug is a program run that violates the specification. And we have a repair tool that automatically suggests repairs, where a repair is a change in the program code resulting in a correct program. We present two approaches to automatic program repair. Both exploit formal verification techniques in a different way. So the first one use Mustfault localization for program repair. We are giving a buggy program, and we do some miracle, let's say, to correct it, and we end up in a patched program that is correct. The patch program has some changes on the code from the original one. So a very useful notion for program repair is the notion of fault localization. Assume again that we are given a program, a buggy program, with a buggy run. And now we apply formal localization to locate the exact location in the program, the exact statement that are responsible for the bug. Actually, it's usually not exact, but it's some set that we suspect are the reason for the bugs. And now the repair can choose one or more of these locations, change them, and result in a correct program. Fault localization should focus the programmer's attention on locations that are relevant for the bug. And if fault localization is too restrictive, then it might miss some potential bug, some potential repairs, while if it's too permissive, it may cause an extra search work. So, and in the literature, most of the fault localization algorithm return a set of locations that may be relevant. It means that no guarantee that all returned locations are relevant, and it is not guaranteed that every relevant location is returned. We, on the other hand, suggest a novel notion of must fault localization. It turns out that in order to define must fault localization, we need to be aware of the repair scheme that we can use. A repair scheme identifies the changes to the program statement that are allowed by the repair. So for instance, we can exchange plus by a minus, greater than by smaller, and a constant C by a constant C plus 1, and so on. Usually this kind of repair scheme is called S-mute, mute for mutations like in genetic works, for instance. So a must fault localization will contain at least one location from any successful repair for the bug. This means that it is impossible to fix the bug using only locations outside of this set. And in other words, any repair for the bug must use at least one location from this set. So this must fault localization focuses very precisely on the bugs. As said, the must notion depends on the repair scheme, and we focus on must fault localization that correspond to a repair scheme, the repair scheme of S-mute. Since we are going to do formal automated program repair, we will have a specification. And a formal specification is such that the program should meet the specification for all inputs. And we are going to use the type of verification which is bounded, meaning that we guarantee the correctness of the program execution, which, for instance, pass through a loop only a bounded number of times. So given a buggy program, the search space for correctness for repaired program are all the programs that can obtain, in our case, by applying some mutation to the programs. And from these, we can generate programs, candidate program one at a time, and check whether they are repaired or not. So we'll have a generate and validate iteration. We will choose from the search space one program, we validate it, and if it's true, we send it to the programmer, and if it's false, we will just eliminate it. We are not building the search space up front, but one after the other, generating and checking for validation. So let's see how must fault localization is constructed by example. Assume that we are given the following program, and now it has a bug, and we'll show a specific bug. Let's say that we start with input in which x is 0 and w is 0, and now assigning t to 0, we have t equals 0 as well. Y gets the value of -3, z gets the value of +3, and now we get to the if statement, and here we see that w, which is 0, is not greater than 3, and therefore this condition doesn't hold. We jump right away to the else. We don't have an else. So after the if, we have an assertion, and when we check the assertion, we see that it's violated because y is now -3, z is now 3, and y is not greater than z. So this is a bug that violates the assertion in the program, an assertion in the program. So the first thing that we do in order to find the fault localization set is to move the program into a single static assignment, SSA form, in which each assignment to a variable is indexed. So for instance, if we have two assignments to T, one in line 1 and the other one in line 5, then the first one will be index 0, and the second one will be indexed 1. And also another thing that we do is to replace every condition by a Boolean variable. And now if we want to know the value of T, let's say, after the if, then we actually have an if then else expression saying that if G0 was true, then the value of T2 is T1, that it got it here, and sorry, and otherwise its value is T0. So we see that again, every assignment gets its own index, and this way, when we check which commands cause y to be greater, not be greater than z0, we have it more precise, because we can know that this depends on y1 and not, for instance, on y0 and so on. So the next thing that we do is to have the indexed program and to construct a dependency graph. And this graph is static. It represents all possible dependencies between variables, between indexed variables. So for instance, we can see here that T1 depends on Z0 and W0 because T1 got assigned by Z0 plus W0. On the other hand, Y2 depends on Y0 only if G0 is false, because we have the definition of Y2 is a kind of if then else, and we see that Y2 depends on Y0 only in case G0 is false. And now we want to be more specific. This is the dynamic graph dependency. And we want to be specific for the fault that we got, for the buggy run that we got. Remember that in this run, this assertion was false, and therefore now we see what kind of variables and then statement influence Y2, and we'll do the same for Z0. So here it is, the set of statements that influence the value of Y2 are those, and the set of statements that influence Z0 are those, and now we map them back to the original statement of the formal, of the program, the non-index, and then we get the fault localization set. This is the set of formulas of statement that cause this assertion to be false. The way we use this Mustfault localization to show its usefulness is to implement it without within multi-return. Sorry, there is a noise somewhere. Am I the only one that hears the noise?
I can hear it as well.
Yeah, someone didn't close its microphone, I guess. Okay, thank you. So we implemented this Mustfault localization within a repair tool called AllRepair, which works in a generate validate form and produce all minimal repairs. Minimality means that a minimal number of repairs of changes is applied. And the idea is that if we can repair a program by changing, let's say, 2 places, then we don't want to a repair that change these 2 places and more. So we focus on minimal. And now the way AllRepair works is to generate a program from the search space, and if it's correct, then we eliminate not just this program, but all the others that are non-minimal with respect to this program. But when we get a program which is not validate, then we don't have any additional reduction for the search space, and we will do it via the fault localization. So here is what we want to do. For the correct mutation programs, we will just eliminate the non-minimal ones. And for the buggy mutation programs, we want to eliminate similar buggy programs, and we'll use the fault localization. So what we'll do, assume that we are getting a program which is buggy, a mutated program which is buggy. We compute its must location set. And now we remember that any program that has this set of statement exactly as in PM will have the same bug, because it is not possible to correct this bug using only a statement outside of this set. And now we can look at all the search space and eliminate from it any mutated program that has this set of statement exactly as in PM. So now we have the following setting. We have a program which is buggy, validation fails, and we also remove from the search space all others similar buggy programs that share the same Mustfault localization. And as before, if the program is true, then we eliminate the one which are non-minimal. And we could prove that the fault localization or repair is sound and complete in the sense that we do not lose any repair that we could get by the AllRepair tool. We didn't lose anyone. And when we compare AllRepair and fault localization AllRepair, we see a significant improvement, and this improvement especially happens when the repairs are slow. They take more than 240 seconds, and here we see that we have a significant improvement, meaning that fault localization indeed pruned the search space, and by that made the whole search more efficient. So just to summarize this part of the talk, we suggest a novel Mustfault localization with respect to a repair scheme. It is must and not may. We must change at least one of the lines return in order to get rid of the bug. And our Mustfault localization significantly speed up the mutation-based automated program repair tool AllRepair without losing any potential repair. So now I'd like to move to another work on repair that use a completely different approach. The goal of this work is to exploit the partition of the system into components and to use a technology, another known and useful technique for verification called compositional model checking that verifies small components and conclude the correctness of the full system. What we add on top of compositional model checking is that if a bug is found, then repair is applied to one of the components. So our setting is CLI communicating systems and a safety specification given as an automaton. So here we have a program. It reads a password, sorry. It reads a password from some environment. It checks whether the password has at least 4 digits. If not, it reads another password and so on until the password is long again. Then it send it for encryption. And this is the way such a program can be described by a control flow graph, but we will actually refer to this control flow graph as an automaton because we want to use a technique of automata learning. Again, a known technique widely used in verification. So here is how we compose programs. We have 2 components, M1 and M2, and they need to synchronize on communication over the same channel, and otherwise they just interleave. So now the first M2 just read the value of XPW from the environment. You can see that in is not a channel appearing in M1, so it just comes from somewhere in the environment. And note that a question mark means that we read information into the variable, and exclamation mark means that we send the value over the channel. So once we read this value for X, the password, we check whether the password is long enough. And when it is long enough, we send it for encryption. And now you can see that we synchronize with the other component, and we send the value of XPW to the variable YPW in M1. Now next M1 do some encoding for Y2, it double it by 2, and then it send it back. So now again we synchronize on the channel get encryption, where now the value of Y is sent to X. So this is the program we will use as example, and the specification will be another automaton, and we can have 2 kinds of specification. First of all, we can have a specification over the sequence of communication. So for instance, we may require that a value for X1 is obtained from the environment before there is a synchronization between M1 and M2 on get encryption. And we may have a semantic constraints that, for instance, requires that the value of X1 before encryption is different than the value after encryption, or that there is no overflow. Here it is, we require that X2 will be smaller than 2 to the 64. And for verification, we will need an error state that sends constraints that are not satisfied to the error state. So now we want to use for compositional verification the method called assume guarantee. And in this method, we get 2 components, M1 and M2, and we want to verify that M1 composed with M2 satisfies P. So the first thing we do is to replace M2 by a small automaton actually, but we call it assumption. And we check whether M1 composed with the assumption satisfies P. since the assumption is much smaller than M2, then we get a much smaller system than if we compose M1 and M2 in full. Next, we see that this assumption correctly described M2, and we check whether M2 satisfies A. Here it actually means that the behaviors of M2 are included in the behavior of A. And if we have these two premises of the rule, then we can conclude that M1 composed with M2 satisfies B. So this is the general rule of using assumed guarantee for verification. We apply the Elstar algorithm for automata learning in order to obtain this assumption. Actually, in the rule that we presented before, the main difficulty is to come up with an assumption that is suitable for the rule. So we come up with some assumption, and then we check whether it's appropriate or not. If it's appropriate, then we can conclude that P holds in M1 composed with M2 without ever composing M1 and M2. On the other hand, if we find a counterexample, we check whether it is real or not. And if it is not real, then we go back and we learn a new assumption, AI plus 1. The same here, if we get this premise, if this premise doesn't hold, then we go back to change the assumption using the automata learning Elstar. If on the other hand, the counterexample is not spurious, so we found a real bug, we add a component of repair. This is our new addition that was not before, was not part of assumed guarantee before. So let's look closer at the Elstar algorithm when we use when we use communicating C programs. Elstar consists, the goal of Elstar is to learn an unknown language L, and it consists of a learner and a teacher. The learner poses questions. It has two types of questions which are answered by the teacher. So the kind of queries asked by the learner is whether a given word is part of the unknown language L, and whether an automaton that the learner produces has its language equal to the language of L. And the Elstar is supposed to learn regular language over finite alphabet, and in order to adapt Elstar to our setting, we will have to decide what alphabet we learn and to make sure that the language we are aimed at is regular. So we actually have an infinite state programs with first order constraints, so it's not so clear how to restrict ourselves to a finite alphabet, but what we do, we just learn statements. We actually learn how the program should look like. So the alphabet consists of assignments and communication actions and constraints. This is the type of alphabet. Word over this represent a computation of the program. And the target of Elstar will have the set of words in M2. M2 is regular since it is itself an automaton. Wow. So now the question is, why should we learn M2? Actually, we know it, and therefore there is no reason for learning M2. But the answer is that the while working on the assume guarantee rule, the assumption we find is much smaller, maybe much smaller than the target. So even though our target is M2, the assumption may be much smaller. So now the learner may ask, is a certain word is part of the language L? Do the following. What happens? Okay. Okay, I'll go on. I hope you hear me.
I think as a host, you have the option of muting participants.
Yes, but
Yes.
then I need to go out of the presentation. Okay, now okay.
It's okay.
Yeah, let's continue. So the learner asks whether a certain word, a sequence of assignment, constraints, and communication action is in the unknown language L, and the teacher do the following. If this word is part of the sequences in M2, it's not part of sequences in M2, then it says no. If it is part of M2 and together with M1 it satisfies P, then this is a good word that we want it to be in the assumption and we say yes. And otherwise, if the, sorry, just a moment, and otherwise it is a real counterexample and we can go directly to repair. Another kind of questions that the learner asks is once it already constructs some assumption, it checks whether this assumption has the language of the unknown language. And now the teacher checks the premises of the rule. If the premises both holds, then it can say that yes. If M1 composed with AI does not hold, then we get a counterexample for this check. And now, if this counterexample is part of M2, then we find a real counterexample and we can go directly to repair. And otherwise, if it's not in M2, then we need to refine AI and to go to build the next assumption AI plus 1. And similarly in the third case. So here we have the setting again of assume guarantee learning, but now we're with repair. And we notice that once we repair M2, we then need to check whether we repaired it fully, whether there are no other errors. And we go back to the assume guarantee rule, but now with the repaired M2. And this process is incremental in the sense that new Elstar starts from result of the previous Elstar. All the questions that we asked before are relevant now. So we repair, the repair is by elimination of error trace, and we have two types of repairs. One is syntactic, and another one is semantic. I'll go to the semantic first. It is more interesting. Assume that we have a behavior of the program that together with the specification just got to the error state while violating x2 greater than 2 to the 64 or violating x2 smaller than 2 to the 64. So what we do, we take the counterexample, which is a run that got to the error state. And for instance, we have a counterexample when x1 equals 2 to the 63. We then form a formula for this counterexample, phi, and we are searching for a constraint that together with phi will result in false, meaning that now the new trace will not be feasible. We'll do it by using abduction. Abduction is a logical technique that can construct such constraints. We use also quantifier elimination and simplification, and the result is a constraint which is x2 smaller than to the 63. This is nice because this is what we would expect as a constraint to make such a counterexample infeasible. So now we will add it into the automaton, but we can also add it into the code as assumption. The place where we put the new constraint is quite arbitrary. We put it along the bad behavior at the end of the bad behavior, but we could choose to put it otherwise, and we need to have to investigate more or where is the best place to put such a constraint. Another type of repairs are syntactic. Again, we got a counterexample and we want to get rid of it. If it contains no constraint, then adding a constraint to it will not eliminate this counterexample. And therefore abduction will not help. So in that case, we either remove exactly this counterexample by means of automata, or we have two kinds of approximation that I will not get into. And we can summarize this type of technique by noticing that in case of that M1 composed with M2 satisfies P, then we are guaranteed to terminate because we use Elstar over finite alphabet. And in this case, Elstar is guaranteed to terminate and return the correct unknown language. Recall that we choose M2 as the unknown language, and in the worst case, we will result in M2 here, which is correct. It's not very interesting, but it is correct. On the other hand, if M1 composed with M2 does not satisfy P, then we cannot guarantee termination because at every iteration we add more and more alphabet. And in this setting, we may not terminate, but we have a progress at each iteration in the sense that we get rid of more and more counterexamples. And in our experimental result, we had one case in which there were infinitely many counterexamples, and it turns out that the repair eliminate them one by one, and therefore we couldn't actually stop. So to summarize, we presented two approaches to automatic program repair based on formal method technologies, and the similarities between the two approaches is that they both handle infinite state C program, and they needed to take care of the syntax of the program, which is the code itself, and the semantics. So we have some checks using SMT. I didn't get into these details, but both the syntax and the semantics are meaningful. Also, they both work in using a generate validate iteration, where the generate produce a candidate program from the space of programs, and the validate checks if the chosen program satisfies its specification. And the two approaches are incremental in the sense that current validation steps make use of previous validation steps, and just this way increases efficiency. The difference between the two approaches is that the mutation-based have a predefined set of mutations for repair, and we will just try them all. Actually, we don't try them all because we prune the state space in order to be efficient, while the abduction-based produce new constraints that are not predefined using abduction. The focus of the mutation-based is the Mustfault localization for achieving efficiency and completeness by pruning the search space, and the focus of the abduction-based is to make validation more scalable by using assume guarantee learning-based paradigm. The mutation-based is supposed to return all minimal repairs, and the abduction-based needs to adapt Elstar to infinite state communicating C programs. The mutation-based use bounded verification, and the abduction-based use unbounded verification. Thank you.
Well, thank you, Orna. That was a very, very interesting talk. Thank you very much. I think we have time for some questions. You can ask the question in person, or you can put it on the chat if you want. Well, I have a few questions to start. Very, very nice, Orna. I particularly like the combination of CGAR ideas and assume guarantee. I think they fit well very nicely. On the first method you proposed, it reminded me of program slicing. And program slicing is simpler than that. I was wondering if you could relate the two methodologies a little bit.
Yeah, so program slicing is closely related to what I showed at first in the general dependency. And also they don't use indexed variable. So let's say that you have one statement in which y get the value of x, and then another statement in which y get the value of z. Then you will, in program slicing, you will determine that x depends on y and z. And here, because of the indexed and because we are more specific, if we have an if then else in between, and we see that according to the condition, x depend only on y, let's say, then we will not get the dependency on z, but we will get a dependency on the condition of the if. And this is essential because we can show that sometimes the only way to repair a program is to change the condition.
I see.
And so for our case, it's important to notice that certain conditions were an important part for the bug.
Okay. Oh, that's interesting. Yeah, I had a student that worked on something similar, a number of years ago. I'll try to find that, see if it's related. If it is, so I'll get to you on that. Might be an interesting extension. Yes. Thank you. I have more questions, but we have one question. Haniel, can you please state your question? So before, sure. Is it Haniel or Aniel?
The first.
Haniel.
Yeah.
Amazing as it seems, Haniel and I are department colleagues, and I haven't met him.
Yeah, right. Yeah, it was all of like 2 months in the university before we had to shut down or something like that.
Yes. Please.
Well, one day. Right. So thanks for the talk, Orna. I had a question related to abduction. So I was wondering what were the limitations in your current setting of the abduction backend that you have?
Actually, we were using Z3 for computing abduction, and whatever Z3 can do, we can do. So this was the limitation, and it is limited.
So do I understand correctly that when you say that you're using Z3 to do abduction, you are relying on Z3 to do quantifier elimination?
We used Z3 for quantifier elimination and simplification, but also Z3 has the possibility to compute abduction.
I see. I was not aware of that functionality.
Yeah. So we are not using abduction in the very traditional way, because usually if you have one condition, you're looking for additional conditions which together are not falsified, and from this you want to imply a third condition, let's say. And here we want them to be together falsified because we want a certain behavior to be infeasible. So the way we used it was somewhat different. Also, the restriction to the set of variables that we wanted was somewhat different from the work, for instance, by Macmillan and Ishil Dilig and Muli Sagiv. But once you give it in a well-defined way to Z3, then you get an answer if it can do it, if it's within its capacity of theory and so on. If you like, I can ask my student to send you the exact way to use it.
Yeah, I was curious because I was not aware of that. One thing I wanted to mention is we had a paper recently on doing abduction inside CVC5, which is the successor now of CVC4, and we do it there based on syntax-guided synthesis. And there we don't have really a limitation of. Sorry.
Based on what?
On syntax-guided synthesis.
Ah, okay. Yes.
And there we have maybe a more general setting than the one that Z3 supports, because we are only restricted to whatever theories are supported in CVC5 itself. So we will not only be able to do it like in linear arithmetic, say, but in all the theories.
Mm-hmm. Okay, it's interesting. I look at it. Thank you.
Yeah, sure.
Marius has a question as well.
Yeah, so this was very interesting work, especially the part on assumed guarantee repair. We were looking together with a student at automated program repair for flaky tests, right? So for tests that very rarely fail, but sometimes mostly they pass. So then they generate a lot of inconsistency. And I was wondering whether could this be applied maybe in some way where you learn automata models from the passing and failing traces, and then with the environment you try to determine, right? Because a flaky test means you have something non-deterministic, right? So could the environment maybe help determinize the automaton and thus generate a fix?
Okay, this will be a different approach. It's very interesting. We were using Elstar as it was not really black box, because we had to do quite a lot of adaptations in order to work on infinite state programs and so on. But essentially, we were using Elstar as a black box. And now what you are suggesting is so the main point is with Elstar is that you have a language, your goal language should be regular and over a finite state. And if you can view your tests as a regular set, then it's okay, and you will get deterministic minimal automaton for this language. But it might be the problem would be to come up with a regular language. It shouldn't be deterministic, but it should be regular. And again, the goal is this language, but the learning can stop earlier, depending on your requirement, of course.
Thank you.
Okay. If there are no more questions, I have one more question. Oh, Gustavo has a question. Gustavo, please go ahead.
Thank you. So thank you, Orna, for a very interesting talk. Have you performed some benchmarks considering real programs to measure the rate of faults detected?
We were running experiments. I'm trying to think. What we were trying to do is to see, to show that we can use abduction to repair, and we had 3 types of syntactic repairs that we were compared to between them. So I'm not sure what your question is.
I was wondering whether you selected some real code and tried to use these techniques to find the real bugs and then measure the rate of the faults detected.
So we didn't use real code. We used some toy examples or somewhat larger, but not real code. No.
Okay.
I think that the bottleneck will be the assume guarantee, because the assume guarantee, it's a very nice idea, but it's not very efficient because of the Elstar and so on. So, but I don't know, it will be nice to make it scalable. Right now, it's not really scalable.
Okay, thank you.
Thank you. And that,
admit that I said that they are test-based and we use formal methods. And in general, the test-based are clearly, they are not as precise in their results, but they are much more scalable because they are based on tests, and it's faster and they can handle larger systems. While formal methods are often restricted in scalability.
and that was actually my question: how fast and how large of a program can you handle? So you answered half of that, I guess.
Yeah, so you will need to go to the paper and look. We have numbers, I don't remember right now, but it was toy or toy plus examples. It was not something from industry that we ran it on.
So lots of future work.
Yes. Lots. Right.
Okay, any more questions? Okay, if not, then we would like to thank Orna for an amazing presentation and amazing work. And it was very nice seeing you again, having you here with us. Thank you very much, Orna.
Thank you. Thank you for inviting me.
And this concludes our session. Thiago, how should we proceed?
Well, since we finished a bit earlier, I talked to our next keynote speaker, and he agreed to start at 10:30. So we can have a half-an-hour break, and then we can start at 10:30, if it's all right.
Okay.
So we're going back earlier than what was established in the program. So on 10:30 we start the next keynote, and then we can have a break now, get a coffee, rest a bit, and then I see you later.
Okay.